So, Chapter 11, Distance Vector Routing Protocols. You got just the briefest of introductions to them a moment ago. So, distance vector routing protocols use the Bellman-Ford algorithm to decipher like which hop should be, or which route should be preferred. Usually for distance vector, it's going to be either Bellman-Ford or Dijkstra's algorithm, which is slightly more efficient. You don't really have to know the specifics on those algorithms, but you can take a look into that if you want to. They periodically broadcast routing updates to neighbors on adjacent links. If the routing metric of a route a router receives is greater than the metric of an existing routing table entry, it is discarded. So in other words, like you say it's based on hop count. You've got in your routing table for a particular network, you've got a route with a hop count of, this would be perfect for like RIP, you've got a hop count of 2. You receive a new routing update for another route to that same network. The hop count on that is 3. Because the hop count is higher, you're going to keep the one that has a hop count of 2, and so you're going to discard that. If it is equal or less, it is added to the routing table. So you've already got one in there with a hop count of 2, 2 routers to get to where it needs to. You receive a routing update that is also 2. Even though you've got one that's already got a value of 2, you're going to add that other one to the routing table as well. So you'll actually have 2 routes to 2 routes to the same network that go a different way. Whenever you get one that is equal, or values that are equal for a route, it'll actually load balance on RIP. At least it'll load balance between those 2 networks. On like RIP, for instance, you can do, I think inherently it's 4 destinations it'll load balance between, but you can actually bump that value up to 6 with some configuration changes. Okay, and this kind of gives you a broad overview of how those routing updates get sent around and everything works. So in this particular network, you've got 4 routers. Each of those has groups of switched networks behind them on the LAN. So for instance, router A, it knows 2 networks directly. That's why you see the C's for connected in the routing table. So it knows about the 172.16.0/16 block that's right over here, and it knows about the address to router B, the 192.168.1.4. So that's why you see both of those in there and the interface that they correspond to. In addition, all of the routes for these other networks are getting advertised out via RIP. So like D is going to advertise the routes it knows out to B. A is going to advertise the routes it knows out to B. C is going to advertise the routes it knows out to B. B is going to advertise out all the routes it knows that it learned that way, except to the interfaces that it learned them from. So B learned about these couple of routes from C. It's going to advertise all of those routes out, every interface except this interface right here where it learned those routes. And same thing on A and D. And so eventually you get a complete routing table, with where it needs to send the data for each respective thing. The R stands for RIP because this is it's a RIP network. And then for routing loops, it kind of gives you an idea. We already kind of touched on this a little bit, but it's not going to advertise out the information on the link that it learned it from to prevent a routing loop. In this particular situation, as soon as this link goes down, if the network doesn't adapt, you're going to have a routing loop. Because, for instance, like D, previously, before this break on the link between A and B went down, it knew that to get to 172.16.0.0, it needed to send it out this interface to B, and then B previously knew that it needed to send it out this interface to A. Whenever that link goes down, though, because of the way the routing table is set up, D is going to send that to B, B is going to send it back to D, and it's just going to keep going back and forth because of the way that the routing table's built. And there's a lot of different ways that the various routing protocols use to try to prevent this exact kind of situation from happening. And these are those ways. Routing loop mitigation. Three main ones for distance vector are counting to infinity, split horizon, and poison reverse. Poison reverse is actually like an addition to split horizon. So counting to infinity, basically what happens is routing protocols count the number of hops to a destination network. By setting a maximum hop limit, we can prevent routing loops. So right here you've got your different routing protocols, and then you have whatever the maximum hop count is. So like for RIP version 1 and version 2, like if a route to get to a network is more than 15 hops, it's going to consider that infinity, and so it's going to expunge it from the routing table. It's not going to be added to there. So like in the situation here, the reason that you had this happen is because like B and D, they're sending these same updates that they learned from A back and forth to each other. Well, each time they send them and they're relearned, it's going to increment the hop count. So at some point, if they're just sending the same routing updates back and forth to each other and they're not learning from a new source like over here, that the number of routing hops is going to reach whatever the infinity limit is for that particular routing protocol, and it's going to remove that route from the routing table. So you probably actually do kind of need to memorize more or less, at least on like these handful of protocols, like what the maximum hop count is. Now on OSPF, it's not a distance vector routing protocol; it's a link state routing protocol. So it doesn't have a maximum hop count; it's set to infinite because it's using completely different values to try to determine like what a preferred route is than the number of hops to get to it. So split horizon, like the situation we had before with these, like learning a route that isn't already in the routing table. So you understand what was happening before is that before A went down, all of these routes had been propagated everywhere. So D had learned about the route to A previously from B and put it into its routing table. But every time like it sends out the routing table, for RIP it's every 30 seconds, it still had that route in the routing table. So it would still continue to advertise it to B because it's still in the routing table. It doesn't know that it's down because it's not directly connected to it. What split horizon does is it doesn't allow a router to advertise routes out of the interface that it learned those on. So in this case, like all of the routes that router D learns from router B, it's not going to advertise those back out to B. Now, if there were other devices connected over here, and you're still going to have route advertisements go down this interface to B, but it's only going to be for routes that it knows from another interface. So anything it learns from there, it's not going to send back. So it prevents those routing updates that may be invalid from going back and forth, like basically two routers telling each other a routing destination that neither of them knows directly and they actually learn from the other. Split horizon prevents that situation. And then by combining split horizon with poison reverse, you can add some functionality to that. Like a router receiving a route update sends the same update back to the interface it originally received it from, but this time with a poisoned route, a route that has a hop metric set to infinity. So whenever we mentioned before whatever the maximum is for a hop count, if you go beyond that, it's set to infinity, so it knows all of the routers that receive that route update know that that's a bad route or a poisoned route. So for RIP, 15 is the maximum. If you set the value to 16 and send that out, all of the other routers know that that is a poisoned route. It's not a route that gets to anywhere, and eventually it'll actually remove it completely from the routing table.